So today we're going to talk about Lesson 4, which is in Unit 1, Inverse Functions. What does it mean to be an inverse? Two relations are inverses of each other if and only, that should be if one relation contains the elements AB and the other relation contains the elements BA. So what's actually happening here? What does that mean? The domain and range switch places. So the domain and range switch places. Okay, still, what does that mean? That means that X and Y switch. Plain and simple, X and Y switch. In other words, the X values of one become the Y values of the other, and vice versa. The Y values of one function become the Y values of the other. So let's look at graphs first. Well, even before we look at graphs, let me go ahead and talk about X and Y switching. So let me just give you a set of ordered pairs. So 1, 2, 3, 4, 5, 6, and 7, 8. So if that's the original function, the inverse function just means we're going to switch X and Y. So instead of 1, 2, we have 2, 1. Instead of 3, 4, we have 4, 3. Instead of 5, 6, 6, 5. Instead of 7, 8, 8, 7. So really all you're doing is just changing the X and Y. Then the other thing I want you to look at is, remember how we were talking about when we looked at a graph, how we could tell whether it was a function by applying the vertical line test. So if I apply the vertical line test to this blue line right here, this parabola, the parabola is a function because it passes the vertical line test. Now I'm not going to make you graph the inverse, but if we did graph the inverse of this parabola, it would be this sideways parabola right here. And this graph right here is reflected over the graph or the line of y equals x. So if I were to take this and fold it along this line, it would end up right here. And as you can see, if I apply the vertical line test right here, it doesn't pass the vertical line test. So we have a function whose inverse is not a function. So that's possible. I mean, you can start with a function and the inverse is not a function, or you can start with something that's not a function but the inverse is a function, or you can start with a function and the inverse is also a function, or you can start with something that's not a function, the inverse is not a function. So you can have all kinds of different combinations. So we're going to apply a new test to determine if the graph of an inverse is a function. So we're looking at the graph of this, which is a parent function of y equals x cubed. And as you look at this graph itself, which is our function, it is a function because if I apply the vertical line test anywhere through this graph, it never touches it more than once. So this graph is a function, so our answer to this one is yes. And the reason is it passes the vertical, I'm going to squeeze it in here, line test. Okay. So then, if I want to look at the inverse, or if I want to determine if the inverse of this particular function is also a function, we don't have to actually graph the inverse. We can apply what's called the horizontal line test. And remember, a horizontal line goes in this direction. And you can see right here that I have placed some horizontal lines through this graph. And no matter where I place a horizontal line through this graph, even through here, it never touches the graph more than once. And so if you think about it, remember the inverse of a function means we're switching the x and the y. So if I use the vertical line test for the function itself, then I can take that function and apply the horizontal line test, which is switching the x and the y. to the graph itself to determine if the inverse is a function without actually graphing that inverse. So on this one, is the inverse a function? The answer is yes. And the reason is it passes the horizontal. So you have to make sure you use the correct test, the horizontal line test. Okay. All right, so let's look at the graph at the right. So as you look at this graph at the right, if I apply the vertical line test through this graph, it never touches the graph more than once. So the graph itself, this blue line, it is a function. So yes, and that's probably not a good color because you can't really see it. So let me switch colors to a prettier one. All right, so this is yes, and because it's to the function itself, I use the vertical line test. So I say it passes the vertical line test. But now if I apply the horizontal line test to determine if the inverse of this graph is a function without actually graphing that inverse, I apply the horizontal line test. I just put one horizontal line through here. Notice it touches the graph in more than one place. As soon as it touches the graph anywhere in more than one place, the inverse cannot be a function because it failed the horizontal line test. So this one's going to be a no. It did not pass the horizontal line test. So on this slide, we are going to look at lists of ordered pairs in a table of values, and we're going to determine the inverse to that function, and we're going to just look at a list of ordered pairs itself. So you can list a set of ordered pairs either like this or in a table of values. They're both identical. I don't want you to forget how to find the domain and range on these. So remember, as I'm looking at this relation right here, this is our domain, and you have to physically list out those values using braces. So I'm just going to do it once for this table of values up here. So let's say I'm trying to write without my palm getting on my iPad. So the domain, you have to use braces when you have a list rather than a graph. So for this one, and I'm going to go smallest to largest and not repeat any values. So I've got -2, -1, 0, 1, and 2. So that's our domain. And then our range, I'm going to put the range up here, are all of our y values, and so you have to use those braces as well. And I'm going to order those from small to large without repeating values. So we've got 4, 6, 8, 10, and 12. Okay, so when you look at lists of ordered pairs, the first thing, remember, you want to look for to determine if it's a function is look at the x values. Do any of the x values repeat? No. So since the x values repeat, then yes, this is a function. And your reasoning is because the x values don't repeat. We can't use a vertical line test on this because it's not a graph. So if I want to find the inverse, notice that now I have an x value, and then this f -1 of x means the inverse of the f function. Well, this is the f function here. To get our inverse, we're going to switch these x and y columns. So I'm just going to put all of these values here and all of these values here. So I'm going to take my x values, and they go in the output, which is our y. Oops, I put x. Ding dong. All right, so I've got -2, and then -1, and 0, and 1, and 2. And then next I'm going to put the y values in where the x was. So 12, 10, 8, 6, and 4. So if I want to determine if this inverse is a function, I can do one of two things. If I physically take this table of values and rewrite it so that I switch the x and y's, then I can just look at the x's and say, oh, do any of the x's repeat? No x's repeat. Therefore, f inverse of x is a function because x values don't repeat. Now, if you didn't want to rewrite this table because it wasn't necessary, and you just want to look at this table of values and determine is the inverse of this function a function, then you're going to have to look at the y values, because remember, inverses switch x's and y's. So instead of applying the test to the x's, you would just apply it to the y's. And remember, those y's became our x's over here. So do any of these y values repeat? No. So you could have just looked at this and said, oh, the inverse of this function is a function because the y values do not repeat. So it depends upon how you show your work. If you don't write this, then you have to look at the y values of the original function and determine if those repeat or not. If you do rewrite the table, then you can look at the x values of the inverse function and say that it is or is not a function based upon the x values repeating. So again, it depends upon what your work is, how you're going to prove it, and what you're going to use. So then you go ahead and stop the video, and I want you to take this list of ordered pairs, and I want you to write the inverse function, and then I want you to determine whether or not this is a function, because this is a relation right now. We haven't determined if it's a function. And then look at the inverse of this relation over here and determine if it's a function. And again, you can use whichever choice you want to, but you have to determine whether you're going to use this to look at the inverse or the inverse function itself to look at the inverse. So go ahead and pause the video and do your work and then restart. Okay, so as I look at this relation, I'm just going to focus on the x values. 1, 2, 3, and 4. No x values repeat, so therefore this relation here is a function because no x values repeat. Okay, even before I write the inverse function over here, if you wanted to, you can determine if the inverse is a function by looking at the y values. So look at the y values, 5, 6, 7, 8. Since no y values repeat, the inverse is also a function. Or you can go ahead and write the inverse over here. So let's go ahead and do that. So I'm going to use braces because I've got a list of ordered pairs. So instead of 1, 5, I have 5, 1. And then 6, 2. And all I'm doing is switching the x's and y's. And then 7, 3. And I'm going to run out of room on the video, so I'm going to put the other one down below. And then 8, 4. And then end those braces. So this is your inverse function. And I know it's a function because on here I could look at the x values, 5, 6, 7, 8, and the x values don't repeat. So if you have this written out and you say the inverse is or is not a function because the x values do or do not repeat, that's okay, as long as you have this written out. But if you're only using this, then you have to look at the y values to determine whether they do or do not repeat. Okay, moving on. Oh, and by the way, I think I forgot to mention, if we haven't talked about it, this is new notation here. I might have skipped right over that. This is new notation. So you might want to write that, new notation. And I know that it looks like f to the negative 1 of x, but it is read f inverse of x. So it is asking you to take the f function and find, write, or graph the inverse of the f function. So that's why we took this f function and just switched the x's and the y's. So whenever we talk about the inverse function, start using this to differentiate between the function itself and its inverse function. So on this slide, we're going to go through the steps to finding an inverse. Given a function, we're going to find an inverse algebraically. So you might want to highlight these steps right here because they are the steps that you should follow, and this is a study issue, so you need to study these. So make sure that you're following each and every step, because this is like a mini proof like you did in geometry. And if you skip steps, it's going to affect your final answer. So here's the steps. We're going to take the function that they give us, and sometimes, as you see over here, so we're going Do example 1 and follow all of these. So sometimes you're going to see f of x, g of x, h of x, whatever the function notation is. Or that just might have a y equals here, it depends. So your very first step is to rewrite the equation in terms of x and y. And all that means is to replace the function notation here with a y, because you're going to have the x there. So in our case for this first step, instead of the f of x, we are going to have a y. So y equals x plus 4. Okay, and so then step 2 says switch the x and y in the equation, and you're only switching x and y. If there's a coefficient in front here, so if this had been y equals 2x plus 4, the 2 would stay here, you would just switch the x and the y, and you'd have an x here and a 2y here. So, and if there's an exponent up there, the exponent doesn't switch, it stays where it's at. The only things that's switching, you're going to exchange an x here and a y here. And why? Because remember, the inverse means that we switch the x and the y. So now we're going to do step 2, and we are going to switch the x, so the x goes here and the y goes here, and everything else stays the same, equals plus 4. So that's your step 2. Then step 3 says to solve the equation for y. Right now it's solved for x. So I want to get y on one side by itself. So to solve this for y, this is my goal, I need to get rid of a plus 4. So I'm going to subtract 4 from both sides. And I get x minus 4 is equal to y. I tend to not like y on the right, so I'm going to switch the left and right sides. So I get y equals x minus 4. Okay, and then we're going to do the final step, and we need to rewrite the equation in terms of f to the negative 1 of x. That just means replace y with f inverse of x. And notice I said f to the negative 1 of x because that's what you think it is, but it's read f inverse of x. So please don't call it f negative 1 of x. All right, so we're going to replace y with f inverse, make sure that's obvious, of x equals x minus 4. So this algebraic equation is the inverse to that algebraic equation. They look similar, but notice that in this particular one we went from a plus 4 to a minus 4. Don't automatically assume that you're going to go from a plus 4 to a minus 4. Each situation is different, so you need to follow these 4 steps to make sure. So we're going to practice that a little bit more in the next 2 examples. So we're going to go to the next 2 slide, or the next slide. Okay, so in this slide we are going to find the inverses of each of these, and we're going to follow those 4 steps that were on the previous slide. So you might want to have those handy to look at. So we are going to start with this function, and then we're going to determine what the inverse is. So that's what it's asking you to find. So you need to know that that notation means find the inverse of the f function. So we're going to replace f of x with y. And so then we have equals 2x minus 2. And then we're just going to switch. The y is going to go here, so you have a 2y, and the x is going to go here. So we're just going to make that switch, so we have an x here and a y here, and everything else stays the same. And then your goal is to solve for y. So this is where my y term is, so I need to get rid of the minus 2. So I'm going to add 2 to both sides. And so then I'm going to continue over here. All right, so then I've got x plus 2 is equal to 2y. I don't like my y term on the right, so I'm going to flip-flop the left and right side. So I get 2y is equal to x plus 2. For our purposes here, you can write your answer in one of 2 ways. So focus on the y. We're solving for y. Y is being multiplied by 2. So to undo multiplication by 2, we need to divide by 2. If I divide the left side by 2, I must also divide the entire right side by 2. So the 2's here are going to cancel. And we're almost done. And so then we end up with y equals x plus 2 all over, because x plus 2 cannot be factored, so I'm going to put that in parentheses, all over 2. I cannot cancel this 2 with this 2 because this 2 is having x added to it. So I can only cancel things that are being multiplied to something else. So these cannot cancel. So that's why I put this in parentheses, because it can't be factored. And I want to make sure that you only understand that you can only cancel an x plus 2 with an x plus 2. So we're not done because we haven't done step 4. So your answer here can be written in one of two ways. You can either write it, so I'm going to run out of room, so I'm going to replace y with f inverse of x equals, so you can either write it exactly as you see it here, x plus 2 over 2, so that's one option, or your other option would be to replace y with f inverse of x and then equals. So if this is being divided by 2, then that means the x is being divided by 2 and the 2 is being divided by 2. So you could write it the following way. X over 2, which actually is in y equals mx plus b form, but x over 2, if you pull x out of the fraction, wouldn't you have a 1 in the numerator and a 2 in the denominator and an x out to the side? So that's x over 2, or 1/2 x. And then 2 divided by 2, 2 divided by 2 is 1. So we would have a plus 1. So that is your alternate way of answering that question. This one tends to lead itself to more errors than this one. So if I were you, I would just leave it that way. All right, so this one looks like it's a little bit more difficult. It's really not. So we're going to go through it together. If you feel confident enough, you could pause the video, do it on your own, and then restart the video and look to see if you did it correctly. So the first step, we're going to replace g of x with y equals x plus 6 over 3. And then remember, we're going to switch the x and y, so the x goes here and the y goes here, and everything else remains the same. So right now, and we have to solve for y. Right now, what we're solving for is imprisoned. It is stuck in this fraction. So remember, to undo that fraction, we have to get rid of this denominator. Because the denominator is 3, we're going to multiply this side by 3 over 1 so that you can easily see that the 3's cancel diagonally. What you do to one side, you have to do to the other. So I'm going to multiply the left side by 3 as well. All right, so then I have 3x on the left equals, and then let's get a different color. Oh, how about this burnt orange? All right, so this 3, so 3 goes into 3 once, and 3 goes into 3 once. And so I'm left with 3x equals just a y plus 6. Right? So now to solve for y, I need to subtract 6, and now I get 3x minus 6 equals y. And I don't like my y on the right, so I'm going to switch it to y equals 3x minus 6. But don't forget, we have one last step to perform. We have to replace y with f inverse of x, and then equals 3x minus 6. And so this becomes our final answer. So on this last slide, we are going to do what's called verify the inverse. We are going to look at two functions and determine, are they inverses of each other? So someone discovered that if we use compositions, we can actually verify this. So we're going to use what you learned yesterday in compositions here. Now, you could take this function and find the inverse of it, just like we did in the last two slides, and compare it to this function. And if they're the same, then they would be inverses of each other, or vice versa. However, you're going to be asked to verify the inverse by compositions. if you take the composition of these two functions, so if you do g of h of x or h of g of x, it doesn't matter which way, and if you get a value that comes out to be x, so it has to simplify down to x, then you can verify that the two functions are inverses. I'm going to require you to do both g of x and h of x, or whatever the two functions are called. I want you to switch the compositions. Just because if you make an error, I want to make sure that you're comparing the two. So just because your first composition comes down to be x doesn't mean you don't have to do the second one. I want you to go ahead and do the second one so you can compare the two and make sure that you didn't make an error. All right, so here's how we're going to do it. So for the first one, I'm going to find g of h of x equals. So our g of x, remember I'm going to write big empty parentheses for my x. So I've got 3/4 big parentheses minus 6. So I'm going to write out that function first, and I'm going to put the h function, because my h function is my input. So this entire h function is going to go in that empty parentheses. So I've got 4/3. That's a 4/3 x. Should have made my parentheses much bigger, plus 8. Okay, so then we're just going to do the math. And remember, this is a proof you're verifying, so you have to show all steps. Less in your head, more on paper, kill a tree. So you want to show everything. So I'm going to distribute all the way through. So I get equals 3/4 times 4/3. They're reciprocals of each other, so reciprocals should multiply to give you 1. So I get 1x. And then 3/4 times 8. So remember, this is 8/1. So the 4 cancels into the 8 twice, and then 2 times 3 is 6. Or you can do 3 times 8 is 24, 4 times 1 is 4, 24 divided by 4 is 6. Both of them come out, whichever way you decide to do it, as a plus 6, right? So that's in parentheses, and then don't forget that minus 6. Now, doesn't the plus 6 and the minus 6 cancel? Yes. So you are going to show that those are canceling, and you must finish it off with equals x. So do you see how the composition of the two functions gave us a simplified value of x? Now we're going to switch it, and instead of g of h of x, we're going to do h of g of x. So here we go. Okay, so now we're going to do h of g of x equals. So my h of x is 4/3, so I'm running out of room, so I'm going to do 4/3, big parentheses, and then plus 8. So that's my h function because it's on the outside, so this is 4/3 x plus 8, right? So our input is g of x, so this entire g of x is going to go in that empty parentheses. So we have 3/4 x and then minus 6. So now we are going to distribute that 4/3 all the way through. So here we have reciprocals being multiplied, so they're going to give you 1 times x is x. So for my first distribution, I get x equals, and then I'm going to multiply the 4/3 to the 6. So remember that 6 is over 1. So 3 divides into 6 twice, and then 4 times 2 is 8, and I have a negative times a positive, so this is a negative 8, and then plus 8. Now remember, you could have done instead 4 times 6 is negative 24, over 3 times 1 is 3. Negative 24 divided by 3 is still negative 8. Then you must continue. These are going to cancel, and we end up with it equaling x. So both compositions gave us x. They complement each other and support each other. Then you have to actually physically say whether it's an inverse, because we don't know that you understand that. So then, based upon your results here, yes, g of x and h of x are inverses. So you have just verified it. Okay, so if you feel confident, you can try number 2 because we have done these compositions before with the square root. If not, you can continue to go through it with me. So you could pause the video, do your work and restart it, or work it with me. Okay, so the first thing I'm going to do is find j of k of x. So my j function, notice, has an x right here. So you're just putting parentheses around the x only. You're hugging the x. So 2 big parentheses squared minus 1. And then our input is our k of x. So this entire square root is going to go in here. So square root of x plus 1 all over, that's a 1, all over 2. Okay, so order of operations say I have to square this before I can multiply the 2 in. I cannot multiply the 2 in and then square that. So we're going to square this first. Whenever you take a radical and square it, you get exactly what's under the radical. So we end up with equals 2 parentheses, and then we square that radical, we get x plus 1 over 2, and then minus 1. Now remember, this is 2 over 1, so that means that this 2 cancels with that 2, and I am left with equals, you can't skip this step and don't do 2 steps in one, x plus 1 minus 1, and then these cancel, so remember it's a mini proof, and then equals x. Okay? Then we're going to reverse it and verify the other composition. So this time we're going to do k of j of x. So our k function is this big square root and then big parentheses for the x plus 1 all over 2. And so our input is the j function, so this entire j function, all of this is going to go in here, which I probably didn't make big enough. All right, so I'm going to put the 2x squared and then minus 1. So there is nothing, so I'm going to work underneath this radical first. There is nothing in front of the parentheses, so I can drop them. And won't the negative 1 and positive 1 cancel? So let's show that these cancel. And so I'm left with equals the square root, because that hasn't gone away, of 2x squared over now 2. And so now, because there's no addition or subtraction, those can actually cancel. And I have equals the square root, don't skip this step, of x squared, and then the square root of x squared is x. So as a result, your answer is going to be, let's use this color. Nope, I don't like that color. Let's choose another color. Okay, let's try that one. All right, so your answer is going to be yes, they are inverses. You know, I can't spell today. And you are done.